Assalamu alaikum, dear students. So we move on to the next topic of the current subject, which is the PN junction. We had been discussing the qualitative aspects of the current flow in a junction in three different categories, namely the junction which is not biased. We had defined that as an equilibrium state of the junction or non-biased condition, and secondly the forward biased junction, and third was the junction which was in reverse bias condition. So let's see what we are going to discuss in today's lecture. This is in the current series of this course, happens to be my 5th lecture, and I do hope that you understood what we talked about in the previous 4th lecture, because this lecture happens to be a continuation of what we learned in lecture number 4. Here again, to give you a flavor of what we talked about in lecture number 4, studying again the physical properties of a PN junction, the so-called interface between two semiconductor materials. On the right side you have the N material, and on the left side you have the P material. The P material, P-type semiconductor, contains holes and acceptor impurities. For the simplicity of our discussion and calculation in the following lecture, we have assumed that the free hole carrier concentration is almost equal to the ionized acceptor impurity. Similarly, on the N-type of the semiconductor layer, the free electron concentration is almost equal to the positively ionized donor impurity. Having made this assumption, our mathematical relations will be quite simplified in a way, and then as we move along for an asymmetrically doped junctions, we can accordingly make various alterations or modifications to our various relations that we will be deriving or have already derived. A junction, as you see in this slide, is characterized by the following, what we termed as the junction characteristics or PN junction parameters, namely one, that due to the diffusion of the majority carriers from P to N and electrons from N to P, as we already discussed in detail, leave behind the uncompensated donor, ionized donor and acceptor layers on the respective sides of the junction. So we have a so-called depletion layer or space charge region just across the interface where the P and N-type material are joined in a PN junction or a diode. And then the same depletion region, the same space charge region has a depletion width designated by letter W, which represents an area or a region in which no free charge carriers can reside, because they will be swept away across on the P and N region by the built-in electric field that is established due to these uncompensated ionized donor and acceptor impurities. Hence a potential difference is established and an electric field comes into being. And finally, we have made some assumptions for calculating the current flow, for the calculation of the quantitative current flow. We have simplified certain values, and I have defined them as an ideal PN junction or ideal diode characteristics by making the following assumptions. Number one, the space charge region between the two sides of diode represents a step junction. What does this mean? This means that the doping concentration from the P side, that the dopant impurity concentration on the P side, which is acceptor atoms, suddenly becomes or reduces in concentration, and on the P side we have, and on the N side we only have donor concentration, positively charged donor ions, and the negligible amount of if there is any acceptor concentration in the n-type region, it is almost negligible. Hence, the point number 2 emphasizes that the junction is characterized, which is our main assumption, that we are using step junction in which the in the depletion region there is abrupt change from acceptor ions on the p side to the donor layer on the n side. Hence, the junction is characterized as an abrupt junction, or in terms of the charge density distribution of the ionized impurities, as a step junction. This is one of the fundamental assumptions that we have made at this point in order to calculate the current and voltage relationship in an idealized PN junction. And number 3 condition assumes that within the depletion region, because there is an electric field present, so if by any chance some minority carriers do happen to diffuse into this depletion region, they will be swept away on the p side or n side respectively, depending upon the polarity of the electric field which is present in this depletion region. Hence, depletion region cannot contain any majority or minority charge carriers, that is, it is completely free or almost free of mobile charge carriers, and that's our assumption number 3, that no carriers exist in the space charge region or in the depletion region. We alternately use 2 terms for this region. Sometimes we refer it to depletion region when we refer to the concentration of mobile charge carriers, namely holes and electrons, and sometimes we refer it to as the space charge region when we are talking about the acceptor and donor ions present in this depletion region. Then another very important assumption that we had made, and I would like to elaborate at this this point now. You see, I just mentioned that there is P region on the left side of the PN junction and there is N region on the right side of the diode. The N region, that is the number of free electrons, number of free mobile charge carriers in the N-type semiconductor material, is almost equal to the concentration of the ionized donor atoms. What does this mean? That each free electron has been obtained by ionizing the atom of the 5th group of the periodic table that we added into the intrinsic semiconductor material in order to make it N-type or extrinsic. Hence, what we are trying to say is each electron that we get in the N-type region leaves behind or comes from an atom which has now been ionized. Hence, it is a positive except donor ion. So therefore, the negatively charged electrons is equal to the positively charged donor ions. Hence, what I have written here, that the neutral N region therefore would be neutral. Similarly, on the P side of the interface, every hole is obtained from the acceptor atom, and hence the acceptor atom becomes negatively charged ion. Therefore, the free charge or free hole concentration in the P-type region is almost equal to the ionized acceptor impurity. Therefore, what I call is that the P-type region is therefore electrically neutral. Thus, point number 4 reads as, in the bulk of diode outside the depletion region, that is on the N side and on the P side, there is electrostatic neutrality. And obviously, as we mentioned in our earlier lecture, that the operation of a semiconductor diode, the current flow, the carrier concentration, and hence the resultant current, magnitude of the current, is very strongly dependent upon temperature. Even we mentioned in our first introductory lecture that semiconductors at 0 Kelvin may be classified as insulator. They are within quotes termed as semiconductors at a finite temperature, which in this course we had taken to be as a reference point the room temperature, which is 300 Kelvin. So behavior of the amount of carrier concentration, free electron and free hole concentration in a given material or in a given diode is subject to variation in temperature. That is, they are highly dependent upon the temperature of the device, and hence the diode operation, that is current in the flow of amount of current flow in the PN junction, therefore would be highly temperature dependent or very sensitive to variation in the temperature at which the diode is held. Number 6 says that in order to obtain an easy flow of current across the junction in a given circuit, we should have very good ohmic contacts at the end of the PN region. What are ohmic contacts? They are points which have very low or negligible amount of resistance, so that current can easily flow from PN junction to outside region in the entire circuit. And then, as I just mentioned in point number 5, point number 7 states that the distribution of carriers, that is how carriers are distributed in semiconductors at a given temperature, because they are temperature dependent, must be calculated in terms of some statistics. And the statistics that we employ, or the assumption that we use, is that the carrier concentrations are subject to Maxwell-Boltzmann distribution. And finally, because I mentioned that we will be talking about the state of PN junction or diode in at 3 different conditions of biasing: no bias, which is equilibrium state, forward bias, and reverse bias. Now, as we mentioned in lecture number 4, when a forward bias is applied across a PN junction, what is a forward bias? A positive terminal of the battery applied potential across p-type region, and the negative terminal of the applied bias is connected to the n-type of the region. What happens to the diode characteristic, the depletion region characteristics? The depletion region across the interface reduces, becomes small in width. The electric field also reduces, and the barrier potential also reduces. So there is reduction in all the junction parameters, namely the depletion region width decreases, the electrostatic potential decreases because of the applied potential across the junction, and finally the electric field also weakens or reduces. Now we have to keep in mind the assumption, underlying assumption is that the amount of reverse bias, or the forward bias in this case, that we apply should be such that the further injection of the majority carriers across the interface between PN and type should be low. We should not have such a large amount of forward bias that there is a tremendous diffusion of majority carriers across the junction. And this type of injection is termed as low-level injection. Let me explain low-level injection further later on in the next few slides. Here is a schematic representation of current flow in the diode that we are discussing currently. On the top of this diagram, you see that the bias has not been applied. So therefore, we use the term the PN junction or the diode under equilibrium state. As you notice that even though we have not applied any external biasing to the junction, yet there is an electric field. You see the electric field direction with the help of our arrow pointing from n-type region to the p-type region. Because why it is pointing from n to p, we discussed that in the previous lecture as well. Because on the n side of the semiconductor region, within the depletion region, there is a positive layer of the ionized impurity atoms. Hence, the electric field is directed within the depletion region according to the polarity of the built-in potential directed from n to p. The middle diagram on the top shows the reverse bias condition. Again, as you notice, the three parameters, the depletion region width widens, the electric field strength increases, and the depletion region potential, the potential across the junction also increases, enhanced by the amount of the reverse potential that you apply across the junction. And finally, we have on the top, you see the forward bias potential, in which a positive polarity is connected to the p-type, and you can compare all the three top diagrams, how these three parameters, namely the amount of built-in potential across the junction varies, how the depletion region width varies, and how the electric field intensity within the depletion region varies according to the applied bias. In the lower portion of the same transparency, we have tried to show you the variation of the current density and the band bending. The band bends due to the fact that now there is a built-in potential within the depletion region, and if electrons from n side further wants to diffuse to the p side region, they will have to do so against the direction of the electric field, which has been shown on top of the slide, and hence there would be a band bending. This band bending reduces in the forward bias direction and increases in the reverse bias mode of the operation of the diode, and then there is characteristic band bending in thermal equilibrium, depending upon, of course, on the doping concentration on the n and p side of the junction. Having revised these parameters, having revised what we talked about in our previous lecture, now we can move on to quantitatively calculating not only the electron concentration but also the amount or magnitude of the current which flows across the junction due to this carrier concentration. And we will be discussing these currents in terms of under three conditions: the equilibrium condition, namely no bias, the forward bias junction, that is a positive terminal of the battery is connected to the p side, and reverse bias when the positive terminal is connected to the n side of the PN junction. Well, here I have shown an idealized current voltage characteristic, and obviously now you would be able to understand that under thermal equilibrium condition, when no bias is applied, of course there is a movement of carriers across the junction. Majority holes diffusing from p to n, majority electrons diffusing from n to p. I've used the term diffusion. Diffusion is the type of movement or motion which takes place due to concentration gradient. I have explained this a number of times in my previous lecture. There is majority of holes on the p side because we doped the material in such a way on the p side to create majority of holes as compared to electrons on the p side. Similarly, n-type comes into being because the dopant impurity has been selected from the fifth group of the periodic table, so that there are more electrons on the n side. Hence there are more electrons on the n side, less electrons coming from thermal generation on the p side. Therefore, there is a concentration gradient. Majority electrons would be moving towards p side where the electrons in minority. Similarly, there are majority of holes on the p side, and they would be moving due to the concentration gradient on the n side, because in the n side holes are in minority. This type of motion due to concentration gradient is termed as diffusion. Hence there is a diffusion current. Now in an unbiased junction, that is junction under equilibrium, which is maintained at a constant temperature, whose value excuse me, we had taken to be 300 Kelvin in this lecture. Under thermal equilibrium, that is under non-biased condition, the total current flow due to diffusion would be exactly equal, but opposite in direction due to equal to the drift current. Hence, even though there is motion or movement of carriers, the majority as well as minority, there would be no net amount of current flow across the junction. Then we move on. We had applied a forward bias. When we apply a forward bias, because of the reduction in the depletion region, because of the reduction in the weakening of the electric field within the depletion region, and because of the lowering of the band bending, more and more electrons and holes will be able to diffuse across the junction, which was stopped in the equilibrium state. Hence the current would increase exponentially. It increases exponentially because earlier when we made the assumption, they followed the Maxwell-Boltzmann approximation, where the carrier concentration as well as the resulting current varies exponentially, which is dependent upon the amount of built-in or junction potential and on temperature. The built-in potential further depends on the doping concentration, and the junction potential therefore would depend upon two factors, namely the doping concentration and the applied bias. So the built-in potential and the applied bias therefore determine how much or how large the forward current is going to be, and it rises exponentially, as you see in this slide, depending upon the temperature. You can control the amount of forward current, which rises exponentially, choosing an appropriate applied bias and choosing an appropriate temperature. This transparency, this slide shows the ideal so-called ideal PN junction. An ideal PN junction is the one whose assumptions we made in the last slide. So you see this exponential rise, but then you also see in the negative quadrant an almost flat or saturated current. This current is termed as reverse or saturated current. Reverse because now the junction has been operated under reverse bias condition. Saturated. Now, what happens in a reverse bias junction? In a reverse bias junction, because the electric field becomes significantly stronger, therefore majority carrier diffusion has been stopped, is almost negligible. But if by any chance some of the minority carriers, that is holes from the N side, happen to come by diffusion within the and land into the depletion region, the electric field present in the depletion region will sweep them across the junction. Similarly, on the P side, the minority carriers are electrons. If these electrons, these minority electrons from the P side, if for some reason they happen to come close to the boundary of the P and depletion region, they will enter into the depletion region and will be accordingly swept to the appropriate side by this electric field present within the junction or depletion region. These, obviously, as the term implies, these carriers which are swept by the field, that is the drift current component, will be small, logically, because the minority is a small number. The holes on the N side are in minority, are in small number. The electrons on the P side are small, therefore the term minority. These minority electrons from the P region and minority holes from the N region will constitute this reverse current, and it is going to be saturated and small, obviously, because the number of electrons moving from P side is small, they are in minority. The number of holes sweeping across the depletion region from N side is small because they are in minority. Hence you see this very small amount of current, which is of the order of microampere. Very small, about 1000 times smaller than the forward bias current, than the forward current. And because the number of minority carrier does not significantly, is very small in the diode anyway, so this current would be small and it will be saturated, because whatever minority carriers there are on the N and P side, only those can drift, and hence the current would be saturated and negative. Therefore, you see almost a flat current on the and a negative current in an idealized PN junction. I have shown you a magnified version of this IV characteristic. You see an exponentially rising current in the forward direction, in the forward bias junction, and a saturated negative current in the reverse bias junction. Then you also notice in this right side of the slide that at a particular reverse bias potential, which I have called as BD, breakdown potential, the current shoots down significantly. This happens, this tremendous or enormous increase in the reverse current at some voltage is termed as the breakdown voltage of the junction. There are special phenomena taking place at the junction breakdown voltage, BD, which we will not explain at this point, and will postpone this in greater detail, the discussion of breakdown phenomena in greater detail in our lecture. But let me just mention at this point the two phenomena which are responsible for this increase in reverse current are termed as the avalanche breakdown or avalanche current, and Zener breakdown or Zener current. We will discuss that in detail in our next lectures. Here again I have shown you a slide in which I am explaining in which I have tried to explain or give the magnitude of the current quantitatively, and you notice that the exponential term, the factor within the bracket, gives you the dependence of the current I on the applied voltage V and temperature T, which you see in the denominator. I0 with the current with the subscript O refers to the equilibrium current. Equilibrium current, as I explained a few minutes before, is the current which flows across the junction in the PN diode when there is no applied bias. So you notice that in the forward bias junction, when applied voltage is positive, a positive terminal is connected to the P side, increases exponentially because of this exponential factor within the bracket. In the reverse mode, this exponential factor would almost be negligible, and hence the current I reduces to minus I naught, and that's the quantitative description of the reverse saturated current. Let me come back to the built-in potential again. Now I have given you a relationship, a mathematical relationship, how the built-in potential is expressed. Quantitatively, we described the existence of the built-in potential due to the uncovering of the ionized donor ions and ionized acceptor ions when the majority electrons diffuse from N to P, or the majority holes diffuse from P to N. On the P side, they leave behind negative acceptor ions. On the N side, they leave behind the positively charged donor ions. This layer of acceptor ions and donor ions constitute a layer of charged atoms, ionized charged atoms, and hence a potential difference is established whose polarity within the depletion region is negative on the P side, positive on the N side. Hence the term built-in potential. Built-in. Built-in means you have not applied any potential across the junction. This potential difference arises due to the diffusion of the majority holes and the majority electrons, as you can see in this slide, across the interface. The amount of the concentration of the ionized impurity atoms, that is the acceptor layer and the donor layer, respectively depends upon the amount of dopant impurity that you have added in the intrinsic semiconductor material. Hence, you see that the term Na, the built-in potential, depends exponentially or increases exponentially according to the added acceptor impurity Na and added donor impurity Nd. Please look at the denominator. There is a term Ni square. What is Ni square? Ni square is the intrinsic carrier concentration. Let me explain this term at this point. When the material was not doped, that is, it was pure, and we have another name for the pure semiconductor material, which is intrinsic. In the intrinsic semiconductor materials, there are obviously electrons, free electrons in the conduction band, and free holes in the valence band, even in the intrinsic, that is pure semiconductor material. Of course, at a temperature, room temperature 300 Kelvin, because at 0 Kelvin there would be no free electrons and no free holes, hence the material would behave almost like an insulator. This carrier concentration is again in the pure material or the intrinsic material, the free electrons in the conduction band and free holes in the valence band. Where do they come from? Because we have not doped the semiconductor material as yet. They come from another process which I defined previously, thermal generation, because we are holding the device, the temperature at room temperature 300 Kelvin. 300 Kelvin. Did you calculate the thermal energy? You should have by now. You know this value. Thermal energy comes out to be 0.025 electron volt, even though it is not a very large amount of energy, but yet it is finite and sufficient to break covalent bonds present in the semiconductor crystal. So because of this temperature, because of this thermal energy, some of the bonds, covalent bonds, break and they generate electrons and holes in pair in equal number. So we have free electron concentration and we have free hole concentration, but this concentration of electron and holes is subject to a law which is termed as equilibrium carrier concentration or law of mass action. Mathematically, how do we define it? The product of free carrier concentration electron, the product of free hole concentration P, N dot P must be equal to Ni square. Ni square is the intrinsic carrier concentration. So in intrinsic material, we will use the subscript I. Ni, that is the electron on the N side, intrinsic carrier concentration electron on the N side Ni, dot Pi, the intrinsic carrier concentration of the holes on the P side must be equal to Ni square, because Ni must be equal to Pi in an undoped or intrinsic semiconductor material. So this is the famous law of mass action. N dot P is equal to Ni square. Let's move on to the extrinsic materials, either N-type or P-type. If you increase the electron concentration in the pure material by doping the impurity from the fifth group, electron concentration obviously would increase and hole concentration would decrease. Similarly, in the P-type material, because you have added the acceptor impurity, therefore holes would be larger than the electron, but yet the product N dot P is equal to Ni square would hold not only on the N-type side of the semiconductor material in the bulk region, but also on the P side of the diode in the bulk region. Hence, this is termed as the equilibrium condition, carrier concentration, and subject to law of mass action, whether the material is intrinsic or material is doped. For the N-type material or P-type material, same law of mass action implies. So you can appreciate quantitatively this built-in expression for the built-in potential. Therefore, it is going to be dependent upon the acceptor impurity that you have added on the P side and donor impurity that you have added on the N side. Ni square being the carrier concentration in the intrinsic material, which I just explained. And Vt is the thermal energy that you get, that the free charge carrier concentration get, or at which it is the temperature at which the diode is held. Having defined this basic parameter, junction parameter, built-in potential, then we can move on to describing how the currents, magnitude of the currents vary in a given semiconductor material under biased condition. One of the simple or first condition that we would introduce at this point is the boundary conditions. What do these boundary conditions imply? They imply that if you, let me take the example of a forward bias because it's easier to explain. Here is the depletion region. On the P side of the depletion region, you have, under forward bias condition, because the depletion region now reduces, the electric field strength now reduces, the band bending also reduces. So because of the band bending, now more electrons are able to diffuse on the P side. So the electron concentration, as you see on the extreme right hand side of the equation in the box, the electron concentration in the P region and subscript P varies or increases exponentially with the applied potential V and the temperature T. And it is also dependent upon the equilibrium carrier concentration. What I'm trying to say here is, if we look into this slide on the right hand side, when there was no applied bias, there was a certain concentration of value of the minority carriers on the P side. This minority electron concentration, which I have designated as N with the subscript PO, that is the electron on the P side in equilibrium, now has increased because of the injection of minority electrons on the diffusion of the minority electrons into the P side. When these electrons come from, when these majority electrons, when they diffuse from N side and enter into the P region, they are termed as minority. They become minority. The majority electrons which started from the N region crossed the depletion region and moved or enter into the P region, hence the term injected, as if electrons have been injected from N side into the P side. On the P side, they will be termed as injected minority electrons. Similarly, injected minority holes on the N side. The concentration of these injected minority carriers depends, as is shown in this equation, on the equilibrium carrier concentration, which in turn is determined from the added acceptor impurity and added donor impurity respectively on the P and N side, and also on the junction potential, applied potential, and also on the temperature. Hence there are three parameters which control the carrier concentration at the edges of the depletion region, and these three parameters are the equilibrium carrier concentration determined by the dopant impurity, the amount of bias applied across the junction, forward biased and reverse biased, and finally the temperature. So you see all these three parameters in the top equation on the right hand side of the box. These are the conditions, boundary conditions, that are applicable in calculating the amount of current that flows across a PN junction. This is the first step that we must understand the boundary condition. Let me begin with, as I just mentioned, we are at the moment discussing a junction which is forward bias. Let me also explain that it would be easier for us at this point to consider only, for example, the motion of electrons. Electrons being particles which we can visualize easily. So let's start. Let's consider only the electron motion across the junction, but obviously the same treatment, the same mathematical results will be obtained for the holes as well. And we are considering an idealized diode in this transparency. So the whole idea of this slide was to give you a flavor of the relationship of the built-in potential and the built-in potential, which I had just shown. And after defining this built-in potential, the amount of minority carriers injected into the P region, minority electrons injected into the P region, minority of holes injected into the N region. When holes from P region are injected due to the forward bias into the N region, they are termed as minorities. So this relationship, these two relationships between the built-in potential and injected minority carriers in a forward bias junction constitute the basic relations in deriving our current, quantitative current flowing in a PN junction. Here is more or less the same result. Using the same assumptions which we elaborated in the previous slides, and as I mentioned again, within the depletion region there would be no current is generated within the depletion region. Why? Because by the terminology, deplete is a region which has been depleted of mobile holes and mobile electrons. So no electron and holes are present there, and if they happen to diffuse from P or N side, they will be swept away by the electric field present within the depletion region. So ideally there would be no current components across the within the depletion region. All the carriers, there will be no carriers, there will be no carriers present, free carriers present within the depletion region. The only carriers which are available are within the P region and within the N region. Hence the carrier motion within the depletion region arises due to movement of charge carriers from P and movement of charge carriers from N. I'm using the term charge carriers at this point because in the P region holes move under diffusion. Electrons in the P region, minority electrons, they move under drift conditions. So the motion of charge carriers takes place from N region and from P region and from N region, and not within the depletion region. They just cross the depletion region. So no current is generated within the depletion region. All currents come from the neutral regions. Similarly, in the neutral N region, there is no electric field. Thus, in the steady state, the solution of the continuity equation with the boundary conditions, which I just mentioned, is given like this. Here I have added a new term, exponential factor, another exponential factor, which is different from your previous term. In the previous slide, you notice that the injected electrons in the P region is dependent upon the equilibrium carrier concentration. NPO is the same term as the minority electrons in the P region, subject to law of mass action, is dependent upon the applied voltage and dependent upon the temperature. Now, this was the boundary condition as it says on the top of the slide. Here is the interface between the depletion region and the neutral P region. When a certain concentration of electrons is injected into the P region, it has its maximum value at some point in space x, which is the interface between the depletion region and the neutral P region. So the maximum value is NP and the equilibrium value is NPO. The amount of increase in amount of this injected carriers, that is how many how many minority electrons has been added, or what is the amount by which the equilibrium minority electrons have been increased with respect to their equilibrium value, is what I have written on the left side of this equation. Now this carrier concentration, the injected carrier concentration, does not remain constant when the carriers now diffuse. Mind you, I'm using the term diffuse because there is no electric field in the bulk or P side of the region, P side being neutral. So these injected carriers now start diffusing across the P side of the region. While they diffuse, while an injected electron diffuses into the P region, it encounters the holes which are present there, and they are majority carriers. So injected minority electrons now see holes present in the P region, and what will they do? Obviously they will recombine, and hence injected electrons start decreasing in numbers. Their number, decrease in number, obviously would depend how strongly the p-type region has been doped, or what is the doping concentration of the acceptor atoms, acceptor ions on the p region. And also it is dependent upon how far the carrier concentration varies, how far the carrier injected electrons, that is, diffuse from the boundary towards the end of the neutral P region. Hence I have defined another term, which is the diffusion length L for the electrons into the P region. So as the electrons diffuse starting from the boundary of the neutral P region and the depletion region, their amount will decrease. The concentration of injected minority carriers will decrease due to recombination process. But this reduction in the carrier, injected minority carrier, is not linear, it is exponential, and it depends on the applied voltage, junction voltage, and applied voltage therefore VA, and at temperature Vt, as we discussed in the previous slide, and also it varies exponentially with respect to the distance that the electron traverses or travels from xn, xn being the starting point in space from P region to some distance P. Similarly, the whole concentration is explained in the lower at the bottom of this slide. Now I have shown this distribution schematically. You see the decrease, exponential decrease of the injected electrons on the P side. I have now reversed my polarity of the PN junction in the previous slide. So on the N side of the junction, the electrons are, the injected holes are decreasing exponentially. On the P side, the injected electrons in the P region are reducing in number exponentially. So exponential behavior is shown in this transparency. Again, the bottom slide I have retained so that now you can correlate the schematic illustration of the carrier concentration schematically as well as mathematically. This transparency shows the magnitude, the quantitative expression for the current densities J in an idealized PN junction. Repetition of the same ideal IV characteristic on the right hand side of the transparency. So there is whole current density on the N side of the PN junction, which is dependent upon, which varies once the whole once the holes enter the N-type region, they would diffuse, and as they diffuse across the N-side region, they would recombine with the holes present there. And due to this recombination, their concentration would decrease. What will be intuitively the amount or the current density? The current density would be proportional to the charges Q, which I have written as E, the carrier concentration of the holes in the N region, which is dP, the small decrease of the carrier concentration, dP, that is gradient, simply the gradient of holes in the N-type region, and finally the diffusivity of the holes. Similarly, for the now I can use the relationship of the concentration gradient in terms of the second term, the exponential factor. So the quantitatively you can define or you can calculate the current density Jp into the N region Xn at any given point Xn, the amount of current density due to holes, which is a function of diffusivity of the holes in the N region, and carrier concentration, equilibrium, thermal equilibrium carrier concentration of the holes on the N side of the region, and finally the diffusion length L of the holes, and it varies exponentially. Hence you see the qualitative behavior of the current in the white box. As I mentioned earlier, that the total amount of current flowing across the PN junction is a sum of two current components, due to holes and due to electrons across the region. The bottom's equation shows this total current density J, which is a numerical sum of the current density due to electrons and within the region termed as minus xp, and whole current density component Jp on the positive side of the. Why xp has been written with a negative sign? Because we take 0, let's say in the space we define x is equal to 0 in the middle of the depletion region. To remind you once again, the depletion region is symmetric because we had taken the ideal condition in which the the dopant concentration of the acceptor Na is exactly equal to the donor concentration on the N side. So Na is equal to Nd, therefore 0, that is x is equal to 0 region, or the point at which x is 0 is in the middle, in an ideal situation is in the middle of the depletion region. Having chosen 0 in the mid of the depletion region, obviously the distances on the p side would be defined as negative distances, therefore p region is defined as minus xp. Distances on the N side would be positive because x is increasing on the N side. So the total current density J is a numerical sum of the current component due to holes and current components due to electrons, and again you appreciate that these are, the variation is exponential, which comes from the fundamental or basic assumptions that the carrier concentrations in semiconductors and hence the amount of or magnitude of current in flowing across the junction would also be subject to the laws of Maxwell's distribution function, and hence their variation would be exponential. Not only depending upon this exponential factor varies according to the dopant concentrations as well as temperature value at which the diode is maintained. Finally, I have shown a relationship for the saturation current separately, which is the saturation current, as I just explained qualitatively, is the amount of current that you obtain in a reverse bias junction. I had been talking about the dependence of temperature so many times in the last few minutes. The carrier concentration in the P and N region, and hence the built-in potential, and hence the amount of currents that flow across the junction, are dependent upon three parameters. This is again a repetition for the nth time. What are those three parameters? The dopant impurity, acceptor impurity on the p side, the dopant impurity, dopant donor impurity on the n side, hence the carrier equilibrium carrier concentrations N and equilibrium carrier concentration P on the N side and on the P side, and they are strongly dependent upon the temperature T. These three parameters had been expressed mathematically in previous 2 or 3 slides. There is another factor which I did not mention before, and this is the junction area, because if the junction area is large across the interface, again current density would be different. Normally in practical diode we choose small area junction diodes, and even in our idealized case we have chosen to have a small area junction area diode. All other factors may be regarded as being constant. However, in this transparency, I'm going to attach some significance to the temperature, because, as I just mentioned, the concentration of acceptor impurity, the concentration of the donor impurities can be chosen at the time of the device fabrication. So they being constant, hence the carrier concentration. If the carrier concentrations are constant, then we have only one factor to tackle with, और वो कौन सा है? वो टेम्परेचर का है, क्योंकि एक दफ़ा आपकी क्रिस्टल बन के आ गई तो डोनर एक्सेप्टर इम्प्योरिटीज़ को तो आप कांस्टेंट तस्वर कर लेंगे, लेकिन आप डायोड की या डिवाइस के टेम्परेचर को तो अपनी रिक्वायरमेंट के मुताबिक, अपने ऑपरेशन के मुताबिक बदल सकते हैं. तो हमारे हाथ में एक बहुत इम्पॉर्टेंट टूल आ जाता है डिवाइस के फंक्शन को चेंज करने का, डिवाइस के ऑपरेशन को चेंज करने का, बाय वेरिंग और बाय चेंजिंग द टेम्परेचर्स, which is not so difficult to do when you are sitting in the laboratory. You can control electrical conductivities by manipulating, that is by changing the temperature over a wide range of values. तो ये बड़ा आसान है टेम्परेचर को वेरी करना प्रैक्टिकल पर्पसेस में, तो इसको मैं खासी इम्पोर्टेंस अटैच कर रही हूँ फॉर द टाइम बीइंग, दैट इज़ टेम्परेचर वेरिएशन इन द डायोड. वही स्लाइड है जिसका मैंने पहले 2-3 स्लाइड्स में जिक्र किया कि आपकी टोटल होल करंट, टोटल इलेक्ट्रॉन करंट, और निचली बॉटम स्लाइड में मैंने दोनों चीज़ें आपको दिखाई हैं कि इलेक्ट्रॉन की डिफ्यूजन करंट पी साइड पे कैसे वेरी करती है, मेजॉरिटी कैरियर्स की होल करंट कैसे वेरी करती है. तो जब आप दो डैश्ड कर्व को और सॉलिड कर्व को कंबाइन करें तो आपके पास एक टोटल करंट डेंसिटी जे की लाइन जा रही है टॉप ऑफ द वाइट बॉक्स में, जो कि पी साइड पे आपको नज़र आ रही है. सिमिलरली आपको एक टोटल करंट ऑन द एन साइड नज़र आ रही है. तो प्लीज़ अप्रिशिएट कि टोटल करंट डेंसिटी एज यू मूव अलोंग फ्रॉम एन टू पी साइड ऑफ द जंक्शन रिमेन्स कांस्टेंट. हालांकि मेजॉरिटी कैरियर कंपोनेंट and minority carrier component on both N and P side are different, yet their magnitudes are such that they compensate each other and the total current in the device remains constant. This is again a very interesting and important result that we have obtained quantitatively, that even though the minority and majority components of current are different both in P and N region, yet the total current remains constant throughout the device. That's a very important result that we obtain. As I just mentioned, that temperature effects are very important, and you notice in the yellow box, you notice that in the denominator of the exponential term there is the temperature term. It is this temperature term in the equation that now controls temperature dependent part of the current density. And I have again repeated the current density due to minority carriers, which is termed as Js. And in the white box on the right hand side, you see the variation in current density at various temperatures. As the temperature increases, your curves shift towards lower values of the applied reverse bias, values of the applied bias. So as temperature increases, your rise, exponential rise in the current curve takes place at lower values of the applied forward potential. The same relation, which I defined as law of mass action, now I have expressed this relation quantitatively, that the product of holes P, NO, NO referring to the N side and O refers to the equilibrium condition, that the holes in the N side, injected holes on the N side, injected holes into the N region, and the acceptor concentration, donor concentration ND, they are subject to law of mass action. That is, minority holes P and O, minority holes in the N region, the majority electrons in the N region, which is the same thing as ND. Similarly, the minority electrons in the P region and acceptor, which is the minority electrons and majority holes on the P region, are subject to the condition which is NA is equal to Ni square, P into ND is equal to Ni square. And the saturation current is strongly dependent, minority carrier concentration is strongly dependent upon temperature. Let me elaborate this point or this mathematical term. Why saturation current is strongly dependent? Look at the bottom portion of the slide, which says Js is proportional to Ni square, and also an Ni square in term is proportional to the band gap of the material and the temperature T. This is a very simple relationship which holds to a certain approximation in the equilibrium condition, that is when there is no bias applied, in the forward bias condition when a forward voltage is applied, and in the reverse bias when a negative terminal of the applied voltage is connected to the P side of the region. What happens? The magnitude of the band gap Eg is not dependent upon the bias, applied bias. So you see the exponential term Eg, and in the denominator you have temperature. What is happening physically to the carrier concentration? What is happening physically to the crystal structure? Let me begin by trying to explain. Please try to visualize a crystal structure in which covalent bonds are bonded. This is a silicon atom, this is a neighboring silicon atom. Their electrons are bonded through covalent bonds. If you increase the temperature, then you can imagine in a crystal in which the electrons are bonded through covalent bonds, the electrons, bonded electrons in the bonds would receive larger amount of thermal energy now as the temperature is increased. Thus, there is a finite probability that these bonds will break and the bonded electron will become a free electron, leaving behind an incomplete bond which is termed as a hole. So electrons and holes are created in equal numbers as the temperature is increased. As the temperature is increased, what follows? Thermal energy that the crystal sees or receives also increases. Electron, due to this increased thermal energy, will break the bond. That's the simple mechanism of bond breaking or the simple mechanism of thermal generation of electron hole pairs in a given semiconductor crystal structure. So this was the concept of bonding in the crystal structure. Now let's try to imagine the same concept in terms of energy band diagram. Here is a conduction band, the top band. Here is a valence band, the bottom band. The bound electrons are represented or reside in the bonded, covalent bonded electrons in terms of the energy band diagram are now shown in the valence band. The free electrons, that is the broken bonds, the electrons which have broken their bonds now after gaining an enhanced thermal energy, now are represented or reside or shown in the conduction band where they are free. The vacancy which the electron has created, or the bond which the electron has broken, now is termed as the hole. So they are electron hole pairs. So therefore you can appreciate that as the temperature increases, there is more and more, the thermal generation rate increases, in simple words. So with the increase in temperature, this thermal generation rate increases. How does it increase? It increases exponentially. And in the numerator you see band gap. So here is a band gap, a certain magnitude of the band gap. As the band gap reduces at a constant temperature, by lowering of the band gap, the thermal generation rate increases. How does it increase? As you can see at the bottom of the slide, it increases exponentially. Keeping the band gap now constant by varying temperature, how do the thermal generation rate increases? It also increases exponentially. So appreciating the negative sign within the brackets, you notice that with the increase in thermal generation, with the increase in the band gap, the thermal generation rate at a constant temperature reduces, because now you require more and more energy which the constant temperature cannot provide. So by increasing the band gap at a constant temperature, thermal generation rate decreases. Now keep one parameter constant, which is the band gap energy. At a fixed band gap, if you increase the temperature, the thermal generation rate increases. So to sum up these two statements, by increasing or decreasing the energy band gap of a given semiconductor material at a constant temperature, we reduce the thermal generation rate. Thermal generation rate increases with the reduction. The thermal generation rate increases with the reduction in the band gap. आपका बैंड गैप डिक्रीज हो तो थर्मल जनरेशन का रेट इंक्रीज करेगा, आपका टेम्परेचर इंक्रीज करे तो आपका थर्मल जनरेशन रेट फॉर ए फिक्स बैंड गैप फिर इंक्रीज करेगा. तो ये दो चीज़ें बड़ी स्ट्रांगली डिपेंडेंट हैं. किस पर? वैल्यू ऑफ द बैंड गैप पर और टेम्परेचर पर, लेकिन एक्सपोनेंशियली. तो एक्सपोनेंशियली राइज करती हैं current density with temperature and band gap. लेकिन जो इंटरेस्टिंग चीज़ आपको यहाँ नज़र आ रही है सबसे बॉटम पार्ट में, कि फिर करंट सेचुरेट कैसे हुई. वो ऐसे हुई कि जो आपकी माइनॉरिटी कैरियर कंसंट्रेशन है मसलन रूम टेम्परेचर पर, वो तो फिक्स्ड है थर्मल इक्विलिब्रियम लॉ ऑफ मास एक्शन की वजह से, तो वो सेचुरेट रही. लेकिन जब आप टेम्परेचर को बहुत ज़्यादा बढ़ाते हैं तो थर्मल जनरेशन रेट बढ़ जाता है, तो उस वक्त आपकी करंट फिर भी सेचुरेट रहेगी, लेकिन उसकी वैल्यू फॉर ए गिवन बैंड गैप इंक्रीज करती चली जाएगी. अब जो चीज़ें हमने पहले डिस्कस की थी वही क्वांटिटेटिवली अब मैं दोबारा रिवर्स बायस कंडीशन में एक्सप्लेन कर रही हूँ। रिवर्स बायस में क्या हो रहा है, आपके वही 3 पैरामीटर्स और फैक्टर्स जो कि डिफाइन करते हैं जंक्शन कैरेक्टरिस्टिक्स को, नेमली जंक्शन पोटेंशियल। नाउ अब जंक्शन पोटेंशियल बायस कंडीशन में 2 टर्म्स पर मुश्तमिल होता है। बिल्ट इन पोटेंशियल आपका पहले ही मौजूद था, जिसकी मैग्नीट्यूड तय किया था आपकी एडेड इम्प्योरिटीज़ ने एक्सेप्टर और डोनर इम्प्योरिटीज़ में, जैसे कि मैथमेटिकल रिलेशंस में आपने देखा। और अब किस पे डिपेंडेंट हो गया कि आपने फॉरवर्ड बायस कितनी लगाई, जो कि बिल्ट इन वैल्यू को डिक्रीज करेगी। आपने रिवर्स बायस कितनी लगाई, जो कि जंक्शन में पहले से मौजूद बिल्ट इन वैल्यू को इंक्रीज करेगी, क्योंकि बिल्ट इन वैल्यू, बिल्ट इन पोटेंशियल की पोलैरिटी और अप्लाइड रिवर्स बायस की पोलैरिटी एक जैसी हैं, तो वो दोनों ऐड अप हो जाएंगी। तो 3 पैरामीटर्स को क्या हुआ, जंक्शन पोटेंशियल इंक्रीज कर गया रिवर्स बायस में, इलेक्ट्रिक फील्ड स्ट्रांग हो गया, इंक्रीज हो गया विद इन डिप्लीशन रीजन, और डिप्लीशन रीजन की विड्थ भी वाइड हो गई, बढ़ गई। तो ये तीनों चीज़ें, तीनों पैरामीटर, मैं फिर वक्त सिर्फ 3 पैरामीटर ले रही हूँ। ऑफ कोर्स चौथा है बैंड बेंडिंग। तो 4 पैरामीटर्स को हम दोबारा दोहराएं। रिवर्स बायस कंडीशन में अप्लाइड रिवर्स वोल्टेज increases the amount of total voltage appearing across the junction. So junction voltage now increases by an amount which is equal to applied reverse bias. The depletion region width increases, the electric field becomes stronger, and the band bending becomes very sharp, becomes very strong. तो आपके पास सिर्फ और सिर्फ अब जनरेशन करंट बढ़ गई। क्यों बढ़ गई, क्योंकि आपके डिप्लीशन रीजन जब बढ़ गया तो एट ए गिवन टेम्परेचर आपकी डिप्लीशन रीजन, चूँकि विड्थ ज़्यादा हो गई डिप्लीशन रीजन में, तो वो कैरियर्स जो कि डिप्लीशन रीजन में थर्मली जनरेट हो रहे हैं, इलेक्ट्रॉन होल पेयर्स मेरी मुराद है, वो इलेक्ट्रॉन होल पेयर्स जो अब इस रीजन में, इस डिप्लीशन रीजन में रिवर्स बायस की हालत में जनरेट हो रहे हैं, तो मौजूद है आपके इलेक्ट्रिक फील्ड डिप्लीशन रीजन में, वो डिपेंडिंग अपॉन द पोलैरिटी इन कैरियर्स को स्वीप कर लेगा अक्रॉस द जंक्शन। तो वो कैरियर्स को जब स्वीप करेगा तो ये जनरेशन करंट अंडर रिवर्स बायस आपकी बढ़ जाएगी, मगर ये करंट जो है ये फिर भी सैचुरेटेड रहेगी, क्योंकि एक ख़ास अमाउंट ऑफ थर्मल जनरेशन रेट एट ए गिवन टेम्परेचर T टेक प्लेस कर रहा है। तो आपके टोटल रिवर्स बायस की हालत में जो करंट डेंसिटी है, जिसको मैंने कहा करंट डेंसिटी J विद ए सबस्क्रिप्ट R, दैट इज द करंट डेंसिटी अंडर रिवर्स बायस कंडीशन ऑफ द डायोड, नाउ विल कंसिस्ट ऑफ सैचुरेशन करंट, जो कि आपकी इक्विलिब्रियम में थी जब आपके कोई बायस नहीं लगी हुई थी। अब बायस लगाने से चूंकि आपका जनरेशन रेट बढ़ गया था, या इलेक्ट्रॉन होल पेयर की कंसंट्रेशन जनरेटेड विद इन डिप्लीशन रीजन बढ़ गई थी, तो वो आपकी जनरेशन करंट कहलाई। तो ये 2 करंट कंपोनेंट्स आपके आ गए, जिनकी वैल्यूज़ मैंने नीचे बॉटम ऑफ द स्लाइड में दिखाई हैं, और टॉप वाले वाइट बॉक्स में वही चीज़ मैंने स्कीमेटिकली इलस्ट्रेट की है, ख़ास तौर पे बैंड बेंडिंग है। आपको शार्पर बैंड बेंडिंग अब नज़र आ रही है। रिकॉम्बिनेशन करंट जिसका मैंने अभी जिक्र किया, वो आपकी फॉरवर्ड बायस में ज़्यादा प्रोमिनेंट होगी। क्यों ज़्यादा प्रोमिनेंट होगी, जैसे मैंने अभी थोड़ी देर पहले आपको क्वालिटेटिवली एक्सप्लेन किया कि फॉरवर्ड बायस में आपका डिप्लीशन रीजन नैरो हो गया, आपका बिल्ट इन पोटेंशियल की वैल्यू कम हो गई, और आपके बैंड बेंडिंग भी रिड्यूस हो गई। तो जब ये सारी चीज़ें हुई कि आपकी रिडक्शन हुई बिल्ट इन पोटेंशियल, जंक्शन पोटेंशियल में नाउ बाय एन अमाउंट इक्वल टू द अप्लाइड फॉरवर्ड पोटेंशियल, डिप्लीशन रीजन विड्थ डिक्रीज हो गई, बैंड बेंडिंग रिड्यूस हो गई, इलेक्ट्रिक फील्ड भी थोड़ा वीक हो गया, तो इसके नतीजे में डिफ्यूजन इन्हांस हो गई, जैसे मैंने पहले 2-3 दफ़ा जिक्र किया। तो जब इंजेक्टेड माइनॉरिटी कैरियर्स पहुंचेंगे ऑन आइदर साइड ऑफ द PNN रीजन, तो रिकॉम्बिनेशन की वजह से उनकी वैल्यू इंजेक्टेड माइनॉरिटी कैरियर्स की रिड्यूस हो रही है। तो वही आपको नज़र आ रहा है यहाँ कि करंट आपकी किस तरह रिड्यूस हो रही है, रिकॉम्बिनेशन करंट की वैल्यू दिखाई है इस ट्रांसपेरेंसी में अंडर फॉरवर्ड बायस कंडीशंस. टोटल अगेन under forward bias conditions, the total current density would be a sum of numerical sum of the two current components, J recombination and J the diode current. Normal diode current जो कि आपकी फॉरवर्ड बायस में चलेगी, और अगर जो रिकॉम्बिनेशन इंजेक्टेड माइनॉरिटी कैरियर्स की वजह से है वो आपके दो करंट कंपोनेंट्स आ गए. एंड अगेन this would be an exponential, the current would rise exponentially depending upon the temperature T in the denominator and depending upon the applied voltage on the numerator VA. और उसकी वही again exponential decrease आपको white box में नज़र आ रहा है. I would now end this today's lecture by summing up what we learned today. We learned mathematically, we derived certain relationships mathematically by assuming a diode which, let's say, we had called an ideal diode, and we saw that when there was no applied bias to the junction, we defined that condition as an equilibrium condition. An equilibrium condition, or a diode under equilibrium condition, is defined as a diode in which the carrier concentrations on the n side of the junction, majority electron and the minority holes, the product of the majority electrons and the product of the minority holes on the n side region must be equal to a constant, and that constant is termed as Ni square. This Ni square, that is the intrinsic carrier concentration Ni, is again a constant, but we have to define this constant with a caution कि ये constant सिर्फ एक temperature पे ये value constant है, जब आप temperature बढ़ाएंगे तो ये constant Ni भी बढ़ जाएगा. तो ये एक absolute constant नहीं है. Ni इंट्रिंसिक कैरियर कंसंट्रेशन कांस्टेंट है एक ख़ास मखसूस टेम्परेचर पर, और लिटरेचर में ये वैल्यू कोट की जाती है, दी जाती है रूम टेम्परेचर पे 300 केल्विन पे. हैविंग डिफाइंड दिस बेसिक assumption that in equilibrium the carriers obey the law of mass action, that is thermodynamic equation n dot p is equal to Ni square. ये तो थी इक्विलिब्रियम कंडीशन डायोड की, या जब कोई बायस नहीं थी. अब जब आप जंक्शन को बायस कर देते हैं, चाहे फॉरवर्ड बायस करें या रिवर्स बायस करें, तो चूंकि जैसा भी एक्सप्लेन किया कि या तो बहुत ज़्यादा इंजेक्शन शुरू हो जाती है फॉरवर्ड बायस के अंदर, या ख़त्म हो जाती है रिवर्स बायस के अंदर, नेग्लिजिबल डिफ्यूजन हो जाती है रिवर्स बायस के अंदर, तो फिर वो डायोड या वो जंक्शन इक्विलिब्रियम में नहीं कहलाएगा. तो फिर हम एक स्टेडी स्टेट की टर्म इंट्रोड्यूस करते हैं कि अब आपको कैरियर्स की कंसंट्रेशन बायस्ड हालत में, और लिहाजा करंट्स की इक्वेशंस जो कि इन कैरियर कंसंट्रेशन से निकाली जाती हैं, अब आपको निकालनी पड़ेंगी स्टेडी स्टेट कंडीशन में. स्टेडी स्टेट कंडीशन में आपको कुछ बाउंड्री कंडीशंस हमने डिफाइन की, जो कि मुख्तलिफ ट्रांसपेरेंसी में मैंने वो बाउंड्री कंडीशंस मैथमेटिकली दी. फिर फाइनली हमने दो कॉन्सेप्ट्स इंट्रोड्यूस किए कि चाहे कैरियर कंसंट्रेशंस हो या करंट डेंसिटीज़, जो कि उन कैरियर कंसंट्रेशंस की मूवमेंट से, मोशन से आपने हासिल की, वो स्ट्रांगली डिपेंडेंट है न सिर्फ टेम्परेचर पर बल्कि डोपिंग लेवल पर, एक्सेप्टर और डोनर के डोपिंग लेवल पे, और जंक्शन एरिया पर भी. तो ये तीनों चीज़ों की डिपेंडेंस कैरियर कंसंट्रेशन पर और टेम्परेचर पर हमने ट्रांसपेरेंसीज में दिखाई, स्कीमेटिकली भी और क्वांटिटेटिवली भी, यानी इन टर्म्स ऑफ कैरियर कंसंट्रेशन, और स्कीमेटिकली उनके ग्राफ कैसे चेंज होते हैं. आखिरी पॉइंट जिसको मैं तफसील में अगले लेक्चर में टच करूँगी वो है जंक्शन रिवर्स बायस का ब्रेकडाउन। शायद मैंने अभी जिक्र किया हो कि हालांकि आपकी रिवर्स बायस हालत में डायोड की करंट कांस्टेंट रहती है और नेगेटिव होती है, लेकिन हमेशा हर वोल्टेज पे कांस्टेंट नहीं रहती। डिपेंडिंग अपॉन द बैंड गैप Eg, डिपेंडिंग अपॉन द टेम्परेचर T, इन दो फैक्टर्स को अगर हम चेंज करें या अगर बैंड गैप की वैल्यू बदल दें या टेम्परेचर को बदल दें या डोपिंग कंसंट्रेशन को बदल दें, तो ये रिवर्स करंट जो है आपकी सैचुरेट नहीं रहेगी बल्कि आपका जल्दी ब्रेक डाउन आ जाएगा। उस ब्रेक डाउन फिनोमेनन को रिवर्स कंडीशन ऑफ द रिवर्स बाइसिंग में अभी इस स्टेज पर मैं उसकी डिस्कशन को पोस्टपोन करती हूँ। तो इंशाल्लाह हम नेक्स्ट लेक्चर में फिर मिलेंगे और मैं आपसे तवक्को करती हूँ कि आपने इस लेक्चर को समझा होगा। अगर कोई मुश्किल पेश आए तो रेफरेंसेस दिए होते हैं, वहाँ से आप पढ़ सकते हैं। लेकिन एक चीज़ को याद रखिए कि आपको अपने क्वालिटेटिव कॉन्सेप्ट्स अगर आपको क्लियर हो जाएं इस सब्जेक्ट में, इन लेक्चर्स में, तो फिर क्वांटिटेटिव कैलकुलेशंस इतनी मुश्किल नहीं होती। दूसरी चीज़ जो मैं आपसे रिक्वेस्ट करूँगी, जैसा मैंने बहुत पहले इंट्रोडक्शन में कहा था कि प्रॉब्लम सॉल्विंग जो है वो बहुत इम्पॉर्टेंट है ऐसे सब्जेक्ट्स में जहाँ आपके या मैथमेटिकल रिलेशंस आए। प्रॉब्लम सॉल्विंग से, न्यूमेरिकल सॉल्विंग से आपकी एनालिटिकल स्किल्स जो हैं वो बड़ी इम्प्रूव होती हैं, एक्सपोनेंशियली इंक्रीज करेंगी, जैसे कि आपने यहाँ देखा। तो वील मीट अगेन। थैंक यू सो मच फॉर योर अटेंशन। अल्लाह हाफिज़।